Welcome. So in today's video, we're going to be discussing p-values a little bit more. So not necessarily in the traditional sense of a normal hypothesis test, but trying to put p-values in the context of something outside of hypothesis tests. I mean, obviously we're going to end up relating them back to tests, but just to give you an idea of how they work, what a p-value actually means, how one should be interpreted, and things like that. So, all right. What we want to consider is, let's say that we have the situation where we have people playing blackjack. Now, we're going to simplify it a little bit and say that, generally speaking, the probability of somebody winning a hand of blackjack is about 46%. Now, realistically speaking, there's a ton of variables that go into this. How many decks you're playing with at the table. The more decks, your percentage of winning goes down slightly. And then other various rules at the table as well. Does the dealer hit or stand on soft 17? Can you double after you split aces, and various other things? If you don't know what I'm talking about, that's perfectly fine. But all of these things, they do change your winning percentage slightly. But to make it a little bit simpler, let's just say that the probability of winning a hand is 46%. Now, what we want to look at in this example, or what I want you to consider, is if we had these four players, and we have this information from these four individuals, does this information indicate that these individuals are cheating? And then lastly, why or why not? So first off, we have that Tyrion wins 188 times out of 400 hands. That would be 47%. Peter wins 135 out of 250 hands. Denarius wins 3 out of 5 hands, and then Podrick wins 16 out of 20 hands. So, if you don't mind, what I'd ask you to do now is take a moment, you can pause the video, and just think about, with each of these four scenarios, with Tyrion, Peter, Denarius, and Podrick, what would you conclude? Do you think that the evidence given is enough evidence that each player cheated? Or, I guess, individually. So we're going to have four decisions there to look at. So again, take a moment. If you want to Google some Jeopardy theme music, have yourself going on in the background, you're welcome to. But take a look at these, and then we'll come back. All right, so hopefully you did that. So first off, we have Tyrion. So Tyrion won 188 times out of 400. Now, that's about 47, or that is exactly 47%, not about. So the question is, do you think this is evidence of Tyrion cheating? Well, hopefully you came up with no. And the reason for that is his winning percentage was really, really, really close to what we would have expected him to win. So we would have expected him to win 46% of the time, which would have been, I guess, 184 hands. He won 188. Well, yeah, okay, he won a little bit more than he was supposed to, but not much at all. Now, how we're going to look at each of these then is not only from that sort of general concept of, okay, if we had this evidence, do we think the person is cheating? But let's also look at it in terms of a hypothesis test. So if we were to conduct a hypothesis test and we used a type 1 error rate or a level of significance of 5% to see if each of the players cheated at blackjack. Well, our hypotheses, our null hypothesis, would be that the person isn't cheating. So if they're not cheating, then their probability of winning, or their overall proportion of winning hands, should be about 46%, because that is our overall probability of winning. If they are cheating, then that means we have evidence that they're winning more than they should, that they're winning more than 46% of the time. So, if we actually went through and conducted this hypothesis test, so we assumed that Tyrion's results were our sample, and we're testing these hypotheses, well, we'd need to calculate our z-value. X, the number of times he won, would be the 188 times n, which is 400, times p naught, which is 0.46, so on and so forth. We get our test statistic value of 0.401. Then, again, if you want to draw the picture, our standard normal distribution centered at 0, we would mark off 0.401, and then we'd find the area to the right of that because we have a right-tailed test. Our alternative hypothesis is greater than, and this area to the right of 0.401 is about 34.5%. Once we have our p-value when we're conducting a hypothesis test, we always compare it to alpha. Our p-value in this case would be greater than alpha, so we would not reject the null hypothesis. So if we think about that in terms of cheating or not, well, the null is that the person was playing honest, that Tyrion was playing honest. Well, we're not going to reject that. So our hypothesis test ended up getting consistent results with what we talked about at the very beginning before we even got to the hypothesis test. That, look, yeah, he played 400 hands, but he only won 47%. That's only 4 more than you would have expected him to out of 400 hands. That's really not that shocking. So no, we wouldn't want to accuse him of cheating. We may accuse him of shooting somebody with a crossbow, but not cheating. So what does this p-value mean? What does this roughly 34.5% mean? Well, if Tyrion isn't cheating, then the probability of him winning 188 hands or more out of 400 simply by random chance is about 34.5%. Now, again, where does this entire statement come from? Well, let's think back to the definition of a p-value. P-value is the probability that the test statistic will take on a value that is at least as extreme as the observed value of the statistic when the null hypothesis is true. All right, well, let's break down that statement a little bit. When the null hypothesis is true. So this last part, well, our null hypothesis is that Tyrion wins 46% of the time. That is what he should win if he's playing fair, if he's playing honest. So that's where the first part of our statement comes from. If Tyrion isn't cheating, or we could say if he's playing honest, however you want to term it, that is when the null hypothesis is true. So that's talking about our assumption. Then it says the probability of him winning 188 hands or more out of 400. So going back to the definition, the probability that the test statistic will take on a value that is at least as extreme as the observed value. So our observed value is the 188 out of 400 hands. Then, at least as extreme, well, that would be the winning 188 hands or more out of 400. So again, just to recap, this p-value, it means that the probability of him playing 400 hands honestly and winning 188 or more, well, that's going to happen more than a third of the time. Well, if something is happening more than a third of the time, then that's not an unlikely event. So we wouldn't want to reject our null hypothesis. In this case, we wouldn't want to reject that he was playing honest and accuse him of cheating. Now, let's look at Peter. So for Peter, we had, he played 250 hands. Out of those 250 hands, he won 135 of them, which would be 54%. Well, if we're looking at that, you should conclude that, okay, that's pretty unlikely because we have really two things. One, we have a pretty good sample size. I mean, we're talking 250 hands. So this isn't something that occurred after just a very, very small number of hands. Secondly, he's winning 54% of the time, whereas he should only win 46%. So when we look at Peter's stats, we probably would accuse him of cheating. Now, if we walk through the hypothesis test, and again, I'm not going to go through every step, but we end up getting a p-value of 0.00554. What that means is, again, if we want to interpret it in the context of the problem, if Peter isn't cheating, so if the null hypothesis is true, then the probability of him winning 135 hands or more out of 250 simply by random chance, well, that's only about 0.5%, give or take. Well, something that's only going to happen about 0.5% of the time, that is an unlikely event. That's not something that we would expect to happen very often. Thus, we do have evidence against our initial assumption that he was playing honest, and we would probably accuse him of cheating. Now, with that said, I'll go on a bit of a caveat outside of the hypothesis test. Okay, it's highly unlikely for someone to play honest and win this many hands or more. There's only about 0.5% chance. Now, if we were actually talking about a real casino, are they going to want to accuse him of cheating just based off of this? Probably not. Because while it's still only 0.5% chance, what that also means, if you want to think about it a different way, is that for every 200 people that play honest, about one of them is going to win this many times or more, simply by random chance, even though they're playing honest. So if you're thinking about it from the casino's perspective, are they going to want to, piss off one out of every 200 players that are playing honest? Probably not. They'd probably want more evidence. But, we're trying to use this just to illustrate p-values. So to look at the other two, so if we're looking at Denarius, so we said that Denarius won 3 times out of 5. Maybe she was playing until she won 1 hand for each of her dragons. Either which way. Now, you may notice when I went to calculate this to find my p-value, I used the binomial distribution instead of the normal distribution. The reason for that is the sample size conditions aren't met here. So if we take, our sample size conditions are that n times p naught is greater than 5 and n times 1 minus p naught is greater than 5. Neither of those are going to be satisfied here. So the way I did it was I just used it as a binomial probability. So again, what is the probability of Denarius winning 3 or more hands out of 5? Well, that would be the probability of x being greater than or equal to 3, which is about 42.5%. So again, something that occurs 42.5% of the time is not an unlikely event. So in terms of the hypothesis test, that is a large p-value. We would not reject the null hypothesis. So we wouldn't want to accuse Denarius of cheating, dragons or not. So hopefully that's the conclusion you came to yourself. Why? Well, obviously 60%, that's much higher than our expected win rate of 46%. However, she won 60% out of 5 hands. So you have an absolutely tiny, tiny sample size. All right, so now we want to look at Denarius. So Denarius won 3 times out of 5 hands. So if we were looking at that before we actually consider going through the hypothesis test, if we're just looking at winning 3 out of 5 hands, is that something unusual? Well, the 60%, obviously that's much higher than the 46% that we would expect someone to win. However, it's only out of 5 hands. So it's out of such a small number of hands that we wouldn't want to accuse Denarius of cheating. Probably wouldn't want to accuse her of cheating anyways if you don't want to get fried. But, we probably wouldn't want to accuse her of cheating based off of this data. And if we actually look at going through the hypothesis test. Now, you'll notice with the previous examples, I actually went through and did the hypothesis test. I found the z-value. From that, found the p-value. Here, we're using the binomial distribution. Probability of success being 46%. 5 hands, so that's our number of trials. The reason we're using the binomial distribution here instead of the normal distribution is go back and check your sample size conditions for using the normal distribution. The sample size conditions are n times p naught is greater than 5 and n times 1 minus p naught is greater than 5. Well, neither of those are going to be satisfied in this scenario. So since neither of those are going to be satisfied, we'll find this using the binomial distribution. The probability of someone winning 3 or more hands out of 5 is about 42.5%. So no, that's not an unlikely event. So even if somebody's playing honestly, winning at this rate is not unusual. Now, the last example we had was Podrick. So Podrick won 16 times out of 20 hands. Now, just on the surface, this one was probably a little more difficult. I would probably say it is, of the 4, the most difficult to just sort of gauge whether or not we would want to accuse the person of cheating. But the reason I included this is in our previous example, our sample size was so small, we said, okay, we couldn't conclude it. Well, that doesn't mean you have to have a huge sample size. Here we only have a sample size of 20. But even if we have a small sample size, if the data is so overwhelming, it is possible to still end up rejecting the null hypothesis. So here, obviously, while it's only 20 hands, he was winning 80% of the time, which is much bigger than the 46% we would expect. With this one, I also calculated it using the binomial distribution. If you would like, this technically would satisfy the sample size conditions for n times p naught and n times 1 minus p naught. So if you wanted to go through as an exercise to go through and calculate this p-value using the normal distribution that we did with Tyrion and Peter to start with, you can. You're going to get a p-value that's pretty daggone close to what we got here. At the end of the day, we end up getting a very small p-value, 0.002. So since we have a small p-value, we'd reject the null. If we want to actually interpret this p-value, what that means is if Podrick isn't cheating, the probability of him winning 16 hands or more out of 20 simply by random chance is only about 0.2%. So that's not very often at all. That's roughly 1 out of 500 times. So that is an unlikely event. Unlikely enough that we would likely reject the null hypothesis that Podrick was not cheating and playing fair in favor of the alternative hypothesis that he was cheating. Now, just like we've discussed before with hypothesis tests, your conclusion is what you come to based off of your data. Does that guarantee that your conclusion is correct? No. In this example with the hypothesis test, we ended up getting a very small p-value. So based off of this data, we would have accused Podrick of cheating. However, even based off our p-value, if the null hypothesis is true, there's about a 1 in 500 chance. Granted, that's really small, but there's still that 1 in 500 chance that someone could win 16 or more hands out of 20 playing honestly, simply by random chance. So is it possible we made a mistake and he was playing honestly? Sure, that is possible. So, all right. Thank you for listening, and that will end our discussion on blackjack and p-values and various Game of Thrones characters. All right, thank you.